Swayam Prabha. Digital India. Educated India.
Hello and welcome back to our discussion sessions on industrial or the production technology, theory and practice. We are calling this discussion series. Now, let me remind you that so far what we have discussed is the mechanism of plastic deformation, and we were discussing that there is a polycrystalline material, and the atoms they make the polycrystalline solid or the polycrystalline material, okay, with the atoms in the equilibrium position as it is shown in this here. And then we said that these crystals are not perfect, that is lattices are not without the imperfection, okay, and those imperfections or the defects, okay. These defects are the point defects, line defects, surface defects. I explained the point defects through vacancy, interstitial or the substitutional impurity, all right. Then there could be a line defect. That line defect in otherwise it is also called the dislocation, okay. And the line defect is that defect if the defect is extending beyond the larger than the lattice spacing. We have a lattice spacing and the defect is extending along the line which is more than the lattice spacing, that is the line defect. And then when it is all along the surface, so that the deformed surface looks like a mirror image of the undeformed surface, this is called the surface defect, or in some cases, I mean some places you will find that this is also known as the twinning, okay, because it is being twinned. So, it is a twinning. So, the deformation also can take place by twinning. All right. Now, the to continue the mechanism of plastic deformation, elastic and plastic deformation can be explained in the atomic scale in this way, that we have the net interatomic force here, for example, and along the y axis, and along the x axis we have the interatomic distance. Okay. Now, interatomic force and the interatomic distance they vary along this line. So, this is the nature of variation of the interatomic force with respect to the interatomic distance, all right. That we have seen that when it is closer the force is more, when it is distance is less force is more, and so on. Now, so suppose the A here, this is the D, this tangent starts, I mean intersecting the 0 level or this x axis at this point. So, that means at this point the attractive force and the repulsive force will be the same, okay. I am talking about this curve if you remember. So, this is the point where the tangent will lie, okay. Tangent will intersect here like here is shown here, and this is the 0 point. 0 point means here at this point the attractive force and the repulsive force magnitude will be the same. Therefore, this distance from here is called the equilibrium distance, okay. Now, suppose the atom has been taken from this position to this position. What does it mean taken? Taken means there is a shear force applied, okay, strain rate applied, and because of the high strain rate the atom in the lattice structure is moved from one position to another position. Let us say from one position is from the equilibrium position, and this has been moved to A, position A. So, A will be moved along this line only, that you understand, okay, because this is the variation between the interatomic force and the distance. So, let us say here now this distance from here dA, if this distance lies within 5% of the dE, not more than 5% of the dE, then upon removal of the external forces which has forced the atom to move from this position to this position, the atoms attain their original position. It will come back to this position. Okay. And this phenomena is called the elastic deformation, because as you understand, the elastic, in the case of elastic deformation, it is linear. Okay. So, in that case the force is removed and the material comes back to the initial length or initial position. All right. So, here also the same thing happens, that if the atom is forced to move to this position, A position, or dA is the distance, and which is less than 0.5, I mean 5%, 0.05 of the dE. In that case, upon removal of the force, the atom will come back to its this position. So, this is the reversible process, which we call as the elastic deformation. Okay. Because there is no permanent deformation. Now, if of course this becomes more than 5% of the dE, then upon removal of external forces, the atoms do not come back to their original position. So, in that case it will be staying here, and the two layers of atoms have moved, that is it. Now, you remove the force and still it will be there, the position will be retained. Okay. That is like in this case as it is shown here. So, initially the forces have been applied, shear forces, and because of the shear force applied, the layers of atoms have moved with respect to each other, and now it has moved to such extent, or the magnitude of the force has reached to that extent, that the plastic deformation started. And upon removal of these forces, you can see that the layers are not coming back to the initial position, they will stay here. So, here this is indicative of the plastic deformation. All right. Had it not been the magnitude had not been so much, that is less than 5% of the equilibrium position, then it would have come back to the initial position upon removal of the forces. Okay. That is the one that is explained here. Next is let us see the amount of shear stress that is required for the deformation, meaning that we are saying that we apply the force, that is very quantitative. How much force you are applying, we have to apply, that we have to see, because we have to accordingly design the machine, because the machine tool ultimately will be involved in removing the material. Okay. What is that the movement of the atom we are talking about, what is the plastic deformation we are talking about? Ultimately we are talking about removal of material, that means initially the plastically it has to be deformed, then it has to be segregated from the main mass. Okay. That is what we are talking about as the deformation. All right. So, therefore, we have to know, instead of saying that qualitatively, we have to know how much force we require, so that the machine tool can be designed, prime mover can be selected, and we can be prepared for the machining to remove the material from a certain workpiece of certain hardness, how much power it will be required. All right. So, let us see how much it is required. Suppose you have the lattice structure like this, the material that has been given for the plastic deformation has the lattice structure as shown here. So, this is the distance, let us say, that has been moved from here to here, okay, because of the application of the shear stress tau. All right. Now, there is a shear stress applied, here the direction is like this. So, this way the shear stress has been applied, and the movement of the, this is the initial position, dotted line, it is shown the initial position of the atom in the lattice structure, and the hatched line is the position it is taking at this moment. So, this layer is moving with respect to this layer. All right. Now, the distance between the two layers is the B, okay, and the distance between the atoms, that is interatomic distance, is A. Okay. So, these are the 3 parameters x, b and a. Now, it has been seen that within the within the atomic distance, okay, a, the variation of the stress with respect to the displacement, this is the displacement, okay. They are related, as you understand, the stress is related to the displacement, because of the stress it is displaced. So, it will be sinusoidal, like this here, it is shown here, and this is one cycle, that is one within the interatomic distance a, all right. Now, this indicates that this is the point which is the maximum stress that is required, and that is what we actually want to find out, that what is the maximum stress required, okay. And this is the shear stress. So, let us assume, or normally it has been seen that this sinusoidal curve can be given if it is a and if it is along the x, okay. It is given as tau is equal to tau 0 sine of 2 pi x by a. So, this is the equation of this curve, since this is a sinusoidal curve, okay, and this is the 2 pi x by a, because this is the a and this is along the x axis, okay. Sorry, this axis is x. X is the displacement, once again I am telling you, all right. A is the interatomic distance, b is the distance between the layers or the layer thickness. For small values of x by a, we can actually say that sine of this is equal to 2 pi x by a, we can ignore the sign. So, tau is equal to tau 0 and the 2 pi x by a, okay. This is for the x by a is really small value, you can see this, the displacement will be in microns. We are talking about the displacement of the atoms, of course, okay, and that would be very small. So, therefore, x by a can be said as a very small value. A sign of small value is that value itself. Now, the strain is given by x by b. Okay. I explained sometimes that if you have a block here, okay, and if you apply the shear stress, the block will be deformed in this way, all right. Let us assume that it will be deformed, and this deformation is in this way. So, how much it has been deformed is this is the x, and the distance between these two layers, this layer is moving with respect to this layer, let us say this is b. So, the strain is equal to x upon b, this much, how much it has been moved, divided by the layer. Let us say this is even in case of the solid material, all right. This is how we normally find out the strain. So, in this case also, as you can see that the strain we have written as x, which is equivalent to this, all right, divided by b, which is equivalent to this distance, all right. So, therefore, this stress, shear stress for small values of the x by a, this is equal to this 2 pi x by a, which is equal to strain into the Young's modulus or the strength of the material, all right. So, this into x by b or the strain is the stress, okay, or in that case we can find out that the tau 0, this is equal to if you take this to this side, it will be g by 2 pi, okay, and a by a, because we are saying that x is getting cancelled and you can see this, okay, g by 2 pi and a by b. Now, let us assume that approximately a is equal to b. We are assuming that it is not very faulty to assume that a is almost equal to b. In that case, tau 0, which is the maximum shear stress required to deform the material, to create the plastic deformation, okay, to create the permanent movement of one layer with respect to another layer of atoms, this is equal to g by 2 pi. Okay. So, if you see, if you look at this equation, this is actually the strength of the material, equivalent to the strength of the material. So, if we take any value of the strength of any material, engineering material, let us say steel, even mild steel for example. Okay. Then you divide by the 2 pi and you will see that this value is very, very high. This value that we are calculating from this, through this, that would be very high. In practice, the shear stress required is much less. What actually we apply is much less than the G by 2 pi, and G, well, G is constant. You understand that this is the strength of material in principle. So, this will be the constant value for the material, and this tau 0 required will be, of course, it is understood that that varies from material to material depending on the strength of that particular material. More the strength, more the stress that will be required. This is obvious. Okay. So, in practice, if we had to apply this much of shear stress, then the machine should have been very powerful. Okay. And it might not have been possible for us to create such a machine so that the so much of stress to be created. What does it mean stress? Meaning that force. Okay. Force by area is the stress. So, area becoming constant, and therefore, the force required would have been very, very high, and force required is very high means we should have a very powerful motor, and very powerful motor will be costlier. So, therefore, the entire process will be very costly, and the product that you are producing by using that machine and with that process will be very costly, and as a result one cannot compete in the market. Now, before I go further why it happens, I should tell you that why we are discussing that, because you know the ultimate aim of machining or any manufacturing process is to produce the end part with the proper shape, size, finish, accuracy and the minimum cost. Right? Cost cannot be very high. In that case, you cannot compete in the market as a producer, as a manufacturer. So, in the cost calculation, we will see that how those factors can be considered. Well, let us come back to this. So, overall, as we have seen that the maximum stress can be found out easily, that is theoretically this is strength of that material divided by 2 pi. All right. Now, why in practice the shear stress required is less? Because we will come back to the defects, because of these defects. Okay. Now, what happens when the shear stress is applied, when there is a defect, and we say that imperfections will always be there in a polycrystalline material. So, instead of the entire lattice structure moving bodily, the defects move. Okay. As a result, what happens, the shear stress which is required will be much less, because the defects or the imperfections, they facilitate the plastic deformation process. So, therefore, instead of G by 2 pi, it will be much less, and how much less, that depends on what is the kind of density of the imperfection and many other factors. So, that can be actually found out, that can be estimated. All right. So, overall what we are saying is that the imperfections actually help in reducing this value. Now, let me give you a kind of analogy. So, if you have seen a carpet being moved, very heavy carpet, let us say this is the carpet, carpets are normally very heavy and it is on a floor. Okay. And let us say it has to, this is a reference line I wanted to show you. So, therefore, I said that this is this thing. So, then let us say this is a carpet and this is on the floor. So, this is the reference line, from here it has to move. So, if you want to move that carpet bodily, it will take a large amount of force and lot of effort, because it will have lot of friction between the carpet and the floor. So, instead of that, if you have seen that sometimes it is actually made like this, okay, meaning that it is done like that, so that a wave is created. Okay, this kind of a wave is created, and then this wave is moved like this, like this, like this, okay. And finally, you will see that this will actually move to, if you see this, let us say this is not in scale. So, it has moved actually this much, okay, from here, from this reference point. So, this is possible to move with the help of this making this kind of a wave, and then instead of the entire carpet moving, you can move the wave, okay. That would be much easier. In that case, the force that is required will be much less. Same thing happens in this case also, that in practice when we do that, since there are imperfections, so therefore, the force required will be very less. As a matter of fact, we will see in one of the processes that the deformation, plastic deformation, when it is made within the layer of almost a perfect material, that is an ideal material, the forces will be very high, and forces are high, that means the power consumption for that process will be very high, because as I said that power is the product of force and the velocity, okay, F c and the velocity V c. Okay. Now, let us come back to that basic machining parameters. So, as we all know, and I also told earlier, that basic machining parameters are speed, feed and the depth of cut. Speed is normally taken in meter per minute, okay, that relates velocity of the cutting tool to the workpiece, that is the primary motion. Now, the primary motion, that is the cutting speed, I narrated it earlier, that in case of turning, for example, it is the workpiece rotates and the tool is given the feed. In case of drilling, in case of milling, in case of the grinding, for example, this is the primary motion or the cutting speed is given to the tool, either to the drill or to the milling cutter or to the grinding wheel, all right, and the feed is given in all these three cases to the workpiece. Of course, in case of shaping, it is to the tool as well, and the workpiece is given the feed. Okay. In case of planing, it is the workpiece is given the movement, which is the primary motion, and the tool is given a feed in that case. It is in the case of the planing. Okay. So, it is given in the unit of meter per minute, as I said. Now, the feed is the movement in millimeter of the tool, okay, in one revolution of the workpiece. Movement is the advancement of the tool per revolution of the workpiece. How much the tool has advanced to the workpiece material. Okay. Now, the depth of cut, it is in millimeter, it is the distance the tool has plunged into the surface. Okay. So, for example, if we have a part like this, okay, and this has been machined like this, let us say, okay, this is a cylindrical job, this is the tool, let us say it is a turning process. Now, this is the cutting velocity which is provided to the workpiece, okay, and this is the feed motion or the feed F, this is the direction of the feed which is given to the tool, all right. Now, this is the initial diameter which we started with, and we are getting this diameter, let us say this is D1 and this is D2. Okay. So, D1 has been reduced to D2. So, therefore, this is the value of the D, which is the depth of cut. Okay. This is the depth of cut. This is the depth of cut, how much the tool has plunged into the surface of the material, okay, which is being machined. Okay. Chip formation, in the case of chip formation, we said that this is the plastic deformation, and finally, it is the fracture, that is in, I have shown it to you in the stress strain curve or the force elongation curve, load elongation curve, that after the point of instability, it goes in a triaxial manner and it fractures. Fractures means that it actually segregates. So, that is the chip formation, we are getting the chip. I once again repeat that. Now, here if you see, suppose we take it in this section, this is the workpiece, this is how the chip is moving along the rake face of the tool, this is the cutting tool, here this is the rake face, this is the flank face, all right. Now, this is the newly formed surface, newly generated surface. This is how the tool is moved, okay, relative to workpiece. So, this is a feed direction. Now, this is the chip motion along the rake face of the tool, as I said, and here is the original surface. So, if you remember, we said that D1 and D2, okay, here. So, this is the original surface and this is the newly generated surface. In fact, what happens is that this diagram that you are looking at, this one, this is a result of the same diagram only when you have a section like this, let us say XX section. If you take a section like this, okay, you will actually see this picture. So, in this picture, since this is the rake face, so that inclination of the rake face is defined by this angle. What is this angle? This is the angle between the rake face and a line perpendicular to the cutting velocity vector. Here it is not shown, but the cutting velocity vector is like this is the Vc, okay. And Vc, as I said, that this is the pi, d and the n. N is the RPM, this is the rotation, here it is shown in this diagram. N is the RPM, d is the initial diameter, and that you multiply by the pi, you will get the Vc, which is the direction like this, right. Okay. So, now perpendicular to the Vc direction, this is the line, between this line perpendicular to Vc and the rake face is the rake angle. So, that defines the inclination of the rake face. Now, this angle, there is another angle between the flank face and the already machined surface, right. So, this is the angle, that angle is called the flank angle. So, flank angle we normally give by delta. So, this is the flank angle. These two angles are very important. In fact, here it is written this is the relief angle or flank angle, both are by both names it is known, okay. So, either it is a relief angle or it is a flank angle, the same angle between the flank face and the already machined surface. This is the line of the edge of the already machined surface. Now, here you can see this line indicates the slip line, and if you remember, I said earlier that the slip line is the line along which the plastic deformation occurs, okay. So, therefore, this is the shear deformation to form the chip, and this is called the shear plane, okay. This is the cutting edge of tool. Now, the shear plane makes an angle with the direction of the Vc. This is also an important angle along with the rake angle and the flank angle. This is parallel to Vc, and this angle is called the shear plane angle. We normally denote that by phi, okay. So, this is the angle between the shear plane and the direction of the cutting velocity vector Vc, this is the phi. So, these three angles, that is the shear angle, rake angle and the flank angle, these three angles are important angles. Now, cutting action involves shear deformation of the work material to form the chip, all right. Now, as chip is removed, the new surface is exposed. So, the chip is removed and the new surface is exposed. This was the old surface, this is the new surface, because the chip, this much material has been removed from this, okay. Now, here if you see, again I am telling you that this is these are the two same pictures, okay. Only thing is that this XX, if you take a section, the sectional view is here. So, if you see that this view and this view is the same. So, this view is nothing but another view of the of this tool. Now, here two things are there, one is new things are there, one is the primary cutting edge, this is the primary cutting edge of the tool, okay, and this is the secondary cutting edge of the tool. Now, the primary cutting edge lead line is actually here, it should be here on this, okay. This is the tool, this is the workpiece, and this diagram I have already shown it to you, that this is the initial diameter, this is the diameter which you have obtained, this is the depth of cut, okay. And if we take the cross section like this will be the view. In this view, this is the rake angle, the same rake angle that I have defined, and this is the flank angle, this is the same flank angle here. Now, this difference between these two lines, and these two lines are the different points of the tool in one revolution of the workpiece, that is the feed, okay. This distance, that is perpendicular to the line, this distance is called the T1, which is uncut thickness. Uncut thickness is given by the feed into cos of the gamma s, and the width of cut is given by the depth of cut divided by cos of gamma s. With this dotted line, this is the next position of the tool that is shown in here in one revolution of the workpiece, as I was telling. So, since the feed is given in millimeter per revolution, so this is the movement of the tool in one revolution of the workpiece. So, therefore, from here to here, this is the value of the feed that can be considered, and this is the direction of the feed. Okay. Again I am repeating with the x cross section, you can get this. So, this is the tool and this is the workpiece. Here this is the rake face of the tool and the inclination of the rake face with respect to the line perpendicular to the cutting velocity vector. This is the cutting velocity vector. This is the rake angle, and between the flank face and the already machined surface, this is the flank angle that has been shown to you earlier. So, this is basically the geometry of the cutting process, geometry of chip formation, and the T1, which actually is the distance between these two lines in perpendicular. Okay. This T1 you can find out from this small triangle, okay, this small triangle, all right. This T1 will be here. So, this is equal to f and the cos of gamma s the side cutting edge angle. So, here the side cutting edge angle is given with the wrong notation. Wrong means not according to this notation. So, if this is the tool in the base plane as it is shown here, this angle is the gamma s, okay. This is the gamma s which is here. So, the T1, this is this value, okay. In this triangle, small triangle, this value is the T1, this is equal to f is this value and the cos of gamma s. Similarly, the width of cut, and the width of cut is actually from here to here, all right. So, this is the width of cut, and this width of cut can be found out from the bigger triangle. From here I am just writing this triangle. From this triangle, if you see, the W will be this value W from here to here, this is the width of cut, is equal to the depth of cut, because depth of cut will be this value, all right, divided by cos of the gamma s. Gamma s is the side cutting edge angle. So, this is the side cutting edge angle. Okay. And as you know that this is the end cutting edge angle. So, these are the cutting edges, okay. This is the principal cutting edge and this is the auxiliary cutting edge as the tool moves in this way, all right. So, therefore, this is the side cutting edge angle, and this is in a particular process, particular method, okay, that we will discuss a little later. So, this is in the coordinate system, in a particular system, and gamma E will be the end cutting edge angle. So, this is the geometry of the process, and in the geometry these are the parameters. T1 is a cutting, it's a geometrical parameter, F is the geometrical parameter, width of width of cut and the depth of cut. So, they are related in this way. So, you can understand that T1 and the W, their product is equal to F into D, all right. So, W T1 is equal to F into D, because cos gamma is getting cancelled. Okay. Now, the cutting tools and the types of machining. If you see this tool, this is a typical lathe tool, and this typical lathe tool can be made from a rectangular shape of the workpiece. As you can see, from here you chop off this much portion, all right. So, this will be the rake face, okay, and this has an inclination. So, that inclination is given by the rake angle, and once again I repeat that the rake angle defining the inclination of the rake face is the angle between the rake face and a line perpendicular to the cutting velocity vector, all right. Here this edge, this is called the principal cutting edge, and this edge is called the auxiliary cutting edge, okay. So, therefore, with this rake face on which the chip will be flowing, all right, we have two faces, principal two faces is the principal flank face here, because this is formed by the principal cutting edge and the auxiliary cutting edge here. So, this is the principal flank face, and here it will be the auxiliary flank face, because this is the auxiliary cutting edge, all right. Now, here this portion which is used to clamp the tool in the tool post, this is called the shank, all right. And here between the principal cutting edge and the auxiliary cutting edge, this is not really a very sharp edge, and normally the nose radius is given, So, that portion is called the nose, and the radius which is given, that is called the nose radius of the tool. And later I will explain it to you why nose radius is important. Okay. This is a 3-dimensional tool, okay, as you can find out from the pictorial view of this tool. This is not very convenient, and it is not actually easy to take this for the analysis, because this has lot of inclinations. You can see that this has more faces. So, the same tool can be represented as a 2-dimensional tool, and here you can see that this is the wedge shaped tool. Here there is a wedge, and this tool can represent easily the same kind of a lathe tool, okay, for analysis, because as you can see that this has an inclination and this is the rake face. This is the flank face of the tool. So, therefore, the inclination of the rake face can be defined by the rake angle, and the inclination of the flank face can be defined by the flank angle. So, therefore, all the basic characteristics of a tool this wedge shaped tool has, and normally from now onwards, whenever we will be using a tool for the analysis, for the ease of analysis, we will be using the wedge shaped tool, because the wedge shaped tool has the required parameters like the rake face, like the rake angle, flank face and the flank angle, all right. Well, so basically all the cutting processes are categorized into two groups. One is the orthogonal cutting and another is the oblique cutting. So, here there is a pictorial view of the orthogonal cutting for you to understand that in case of orthogonal cutting, the cutting edge of the tool, you see this is also a wedge shaped tool like this. So, this is the cutting edge of the tool, this is perpendicular to the direction of the cutting velocity vector. So, the cutting velocity vector and the tool edge, cutting edge makes a perfect 90-degree angle, they are perpendicular to each other, all right. So, therefore, what happens in this case, if you look at this system of axis, let us assume that we have taken x, y, z this way. So, since it is strictly perpendicular to the direction of v, that is the cutting velocity vector. So, therefore, all the forces will be confined to the x z plane, okay, and the chip will be flowing exactly along the z axis, okay, or the x z plane. All right. There will be no inclination of the chip from the z axis, because the cutting edge is exactly perpendicular to the cutting velocity vector. So, when this condition satisfies, so in that case we can call that as an orthogonal cutting. So, since all the forces will be confined to one plane x y x z plane, so therefore, this condition or this kind of a process is called the two dimensional process, okay, because here the chips will be flowing in one dimension, that is in the x z plane, all right, exactly along the z plane. This is perpendicular to the cutting velocity, cutting edge, all right. But when the tool edge is inclined with respect to the cutting velocity vector, as you can see from this diagram, okay, that the tool edge which is here, this is inclined with respect to the cutting velocity vector by an angle of this, okay, I, this is called the tool inclination angle. So, in that case, this kind of a process or cutting process is called the oblique cutting, okay. So, in oblique cutting, apart from the tool being inclined, or rather we will say that because the tool is inclined with respect to the cutting velocity vector, then the cutting is three dimensional, because the cutting forces will be now located in all planes like x, y, z plane, okay, and the chip no more be flowing exactly perpendicular to the cutting edge, but it will be inclined to the with respect to the z axis and inclined to that side where the resistance to flow will be less, that we will discuss later. So, right now we should understand that since it is inclined, so therefore, cutting forces will be located in all x, y, z plane, and the chip will be flowing not perpendicular to the cutting edge, but inclined to the z axis. It will not be flowing in x, z plane anymore, like in the case of the orthogonal cutting. Therefore, this condition is the three dimensional case, and as you understand that in case of tool when it is inclined, when it will approach the workpiece, it will grab the workpiece gradually, okay. Can you see this? Like if when in case of orthogonal cutting, when the tool is approaching the workpiece, it will grab the workpiece all at a time, the whole entire cutting edge will be grabbing the workpiece at a time. Whereas, in case of oblique cutting, okay, the material will be grabbed gradually because it is inclined, and therefore, the tool strength available will be more. Okay. So, for this purpose, the oblique cutting is normally used in practice, all right, and you will see in all practical purposes the cutting processes are oblique cutting, okay, where the tool is inclined with respect to the cutting velocity vector. Probably one example that I remember or that comes to my mind at this moment is this. Let us say if we have a workpiece like this, all right. Suppose the workpiece is this, which is mounted in the 3-jaw chuck, okay, and this is the workpiece. Let us say this is a cylindrical workpiece mounted in a 3-jaw chuck, and this is the tool, okay. This is the tool which is given a feed, and this is rotating, all right. So, this is an example of the orthogonal cutting. As you can see that this in here is a straight one, all right, parallel to this. So, therefore, the cutting the chip will be flowing exactly along the x z plane or the z axis, okay. This will be perpendicular to the cutting edge, but for any other cases the chip will be not flowing perpendicular to the cutting edge, but it will be flowing along the all x y z plane, and therefore, all other cutting processes will. Okay. Now, now that we understand the difference between the orthogonal cutting and oblique cutting, we will see the type of chips. All right. So, initially if you remember, I told you that depending on the cutting parameters, depending on the workpiece, depending on the combination of the workpiece and the tool material, all right, depending on the tool geometry, we have different types of chips. And by the chip morphology or the type of the chip that is being produced during the process, you can actually diagnose many of the things about the process, okay, and you can improve the process by improving some of the parameters. Okay. So, one type of chip is the, let us say we will start from here, one type of chip is a continuous chip. Okay. So, in case of continuous chip, when the continuous chip occurs, when the material, workpiece material is ductile particularly. Okay. Now, other factors which affect the formation of the continuous chip are the high cutting speed, small feeds and depth of cut, large rake angle, this rake angle has to be large, sharp cutting edge, okay, cutting edge cannot be rounded off, low tool chip friction, that is the friction, coefficient of friction between the rake face of the tool and the chip should be low. In that case, the continuous chip will occur. So, continuous chip is that it will be produced because it is a ductile material and it will be continuous flowing along the rake face of the tool and it will curl. So, continuous chips need to be broken because chip we cannot we cannot permit the chip to be infinitely continuous. In that case, what will happen is it can entangle with the workpiece, it can entangle with the tool and it can actually rub the workpiece, it can rub the tool, spoil the tool angle, spoil the already machined surface, precision and so on. So, therefore, when there is a ductile material which is used as a workpiece material, then we need to have the chip breaker. Okay, the chip has to be broken. So, chip cannot be broken all the time manually, you understand. So, there are different kind of chip breakers which are normally installed on the on the rake face of the tool, and when the chip is being formed, it will hit the chip breaker which will be basically a protrusion on the rake face and it will get broken. Okay. Or we can have, for example, deliberately if we put a crater kind of thing, I am just exaggerating, suppose there is a crater deliberately made on the tool rake face. In that case, when the chip will be formed, it will actually go along with the crater, it will curl more and this crater will facilitate the chip to be broken. So, either way the chip can be actually broken, which is advantageous in our case, because in that case it will not be disturbing the cutting process. So, once again ductile workpiece material, high cutting speed necessary, small feed and depth, large rake angles, sharp cutting edge and the low cut chip tool friction, coefficient of friction. These are important parameters for which the continuous chips occur. Another type of chip, when the workpiece material is brittle, in that case the chip formed is discontinuous. It cannot have a continuous chip, because if you remember from the stress strain curve, okay, I will just remind you that this is the stress, this is the strain, and for brittle material it will break here. It will not go to the plastic zone. It will only be elastically deformed, and then if we increase the load or increase the stress, it will be broken. So, therefore, once the material, workpiece material is brittle, in that case the chips will be broken, all right, and the discontinuous chip will be occurring, which will be flowing again and coming out from on the rake face of the tool. So, the conditions which should be met for the discontinuous chips to occur, these are the brittle workpiece material, as I said, like cast iron for example, this is a representative material for the brittle material. Low cutting speed, here it was the high cutting speed, so it is opposite to that. In fact, all the parameters are opposite to the condition for which the continuous chips occur. Large feed and depth of cut, small rake angle, high tool chip friction. So, when all these factors exist, then the chip will be discontinuous chip. Okay. Chips produced will be discontinuous chip. Now, is there any benefit, is there any advantage of the discontinuous chip? I told you one disadvantage of the discontinuous chip, continuous chip for example. So, therefore, in the case of discontinuous chip also we will have some kind of advantages and some disadvantages. So, advantages you can understand that since chips are breaking, so majority of the heat will actually go away with the chips because it is broken and it is not in contact with the tool. Here if you see the continuous chip since it is flowing continuously, it is always in contact with the rake face of the tool. So, therefore, the chip which is very hot, I repeat once again, hot because of the plastic deformation in the shear zone, and additionally because of the friction between the chip and the rake face of the tool. So, that heat will be conducted to a large extent to the tool because the chip while flowing is in direct contact with the tool all the time because it is a continuous chip. Whereas, in case of discontinuous chip, since the chip is breaking, so it is not in constant touch with the tool and that much of heat will be conducted to the tool. Second thing, this you can take as an advantage of the discontinuous chip. Now, the disadvantage of the discontinuous chips, that each time the chip breaks, it actually gives a kind of an impulse. Okay. So, there could be a fluctuation in the force, cutting force, and that actually can have some kind of a feed mark on the already machined surface. So, this is a disadvantage while the discontinuous chips occur. Now, the third kind of chips, this is the continuous chip with the built up edge. Okay. Built up edge is called the BUV in short form, which is very popularly expressed. Now, built up edge happens like with a certain condition of temperature and pressure, okay, not all the time, with certain condition when the pressure and the temperature reach a certain level, then instead of chip flowing along the rake face of the tool, a very thin layer from the chip will be removed. Okay. So, because it is a very high pressure and very high temperature, and the pressure is maximum at the tool tip. All right. Similarly, at that temperature and pressure, a very small layer from the rake face of the tool will also be removed because of the again high strain rate of deformation, high pressure, high temperature, okay, at a certain level of speed, cutting speed. All right. Now, since the chip surface is nascent because a thin layer has been removed, and the rake face surface is nascent also because the thin layer also has been removed from there. So, these two surfaces will have the affinity to each other and they will try to get welded. Okay. As they get welded, in that case there will be further position, or this will restrict the flow of the chip along the rake face of the tool because it is welded. So, it will resist the flow of the chip. All right. So, therefore, what happens that chip will not be able to flow and it will actually pile up. Okay. So, this piling actually will further resist the chip flow, and that piling which actually is the welded junction, and that piling will grow. Okay. That piling will grow in front of the tool tip, and when it will grow to a sufficient dimension, sufficient size, it will be unstable and it will break. All right. So, when it breaks, if the same condition of the temperature and pressure exist, then again it will start getting piled up because those two nascent surfaces again will be welded. All right. Then again it will be resisting the chip flow. So, chip instead of flowing along the rake face of the tool, it will get resisted and it will pile up in front of the tool. So, finally, what happens is that if this is the tool, so in front of the tool it will be piling up, I am exaggerating, like this. Okay. So, in this case it will be something like this, it will be piled up. All right. So, this piling in front of the tool, this is called the built up edge. Okay. Now, when it is breaking, you can see that part of this will be remaining on the already work surface. This is the already work surface, and part of it will be embedded in the chip, and it will also be on the tool tip. All right. Now, what does it mean it will be on the tool tip is that the tool angle will be different, because once it is piled up here in front the edge of the tool, in that case the rake angle as well as the flank angle is changing. Moreover, since it is dynamic process, meaning that the built up edge is piled up, it is getting bigger and bigger, then it is actually breaking, and again it is a small, it started being built up. So, therefore, this is dynamic, and all the time this rake angle and the flank angle will be changing. I will tell you later on, I will derive, I will show you that as the rake angle changes, the cutting force also changes. Cutting force changes means the power consumption changes. All right. In that case, what will happen? The cutting force will fluctuate, all right, because of the change in the rake face of the tool. So, therefore, the cutting process will not be perfect in the sense that surface finish may be affected because of that. So, this is a disadvantage of the built up edge formation, and therefore, we should actually avoid getting the built up edge. And as I said that part of the built up edge will remain on the workpiece surface. So, it will spoil the surface finish of the already machined surface, of course. So, that is another disadvantage. And what happens is that the here it remains on the tool because of this reason. So, let us say this is the tool, okay, and here I will exaggerate, this is the piled up built up edge. Okay, you can all see this, right. Now, the built up edge is actually a material which is very hard material, because it is strain hardened material, okay, because chip is being the hard strain hardened, and this material which is getting because of the thermal because of the plastic deformation. So, this is a strain hardened very hard material, it is getting piled up at the in front of the tool. So, when it breaks, actually what happens is that if we draw the curve of the along the rake face of the stress, the stress is maximum here, because at the tool edge, okay, at the tool tip here the pressure is maximum, force is maximum. So, therefore, the stress maximum here, and the resistance to the shearing of this when it is sheared off will be maximum along this line, okay. Whereas, as you go inside this, the hardness will be less, okay, because of this curve, as you can see this. So, therefore, the resistance to the plastic to the shearing will be less along this. So, let us say this is A, this is B, and this is C, okay. So, resistance along the ABC will be less, because the stress is maximum along the AC, okay. Let us say this is A. So, therefore, when it will break, okay, when this piling built up edge will break, it will actually break along this, along the ABC, and not along the AC. Had it broken along the AC, in that case, of course, it would not have been stick to the rake face of the tool. So, since it is breaking along the ABC, so it will remain there, it will pile up. So, this will actually spoil the geometry of the cutting tool, particularly the rake angle and the flank angle, and there will be a fluctuation of the force, okay. So, I hope this is understood that this is the mechanism of the built up edge formation, and the mechanism of built up edge formation, I would like to repeat that it will not form all the time. I said that for a particular condition of temperature and pressure. Let us say, for example, in case of combination of high speed steel and the mild steel is the workpiece, let us say, okay, and this is the tool material, high speed steel. For this combination of the tool and the workpiece, this cutting velocity between 80 and let us say 110 meter per minute, this is the range at which, for this particular combination of materials, tool and the workpiece material, at this range of the speed, the condition happens when the thin layer will be ruptured from the from the chip and a thin layer will be ruptured from the rake face of the tool. Okay. And when this cutting speed goes over 110, so this situation does not happen. Why, I will explain it to you in our next session of discussion. Thank you very much for your attention.